Suppose we have a population that grows at a constant continuous proportional rate, say 5%, and suppose that we start with 100 individuals. We can ask questions about the future behavior of this population, questions like how long will it take for this population to double, and what's the long-term behavior of the population. So with this sort of setup, we can write a differential equation to describe this population, because this phrase, constant continuous proportional rate, right, growing at a constant continuous proportional rate, if we call P of t the size of the population at time t, then a constant proportional rate, well, a proportional rate is the rate of change of the population, which is dp dt, divided by the size of the population. And if it's growing at a constant 5% per year, then that means this ratio has to be equal to 0.05. And so you can see this is a differential equation. In fact, if we multiply both sides by p, we get dp dt equals 0.05 times p. And this is actually a really nice differential equation. It's separable in particular, so we could separate the variables in the usual way, divide both sides by p, multiply both sides by dt, so divide by p, multiply by dt, like this. Then on the left-hand side, the dt's are gone. On the right-hand side, the p's are gone. And we get dp over p equals 0.05 times dt. And then we can integrate on both sides. On the left-hand side, we get absolute value of p. On the right-hand side, we get, natural log absolute value of p. On the right-hand side, we get 0.05t plus a constant. Then we can exponentiate. So we get absolute value of p is equal to e to the 0.05t times e to the c, but I'm going to call e to the c a. And a has to be positive because it's e to the c. But then when we remove the absolute values from the left-hand side, that essentially gives us a plus or minus on the right-hand side. But we can absorb that plus or minus into a by removing this requirement that a be positive. So then we get p is ae to the 0.05t. As usual, the constant of integration when we solved turns into the parameter that describes the family of solutions to the differential equation. Remember, we also had a data point. We know that the initial population was 100, so p of 0 has to be equal to 100. But that's a times e to the 0, so that's just a. So a is 100. So p of t is the function 100 times e to the 0.05t. It's fine. So no big surprise here, right? When you have constant proportional growth, continuous growth, you get an exponential function. So now we can answer all sorts of equations about this population. For example, how long does it take to double? Well, if it starts at 100, then doubling would be 200. So we can say 200 equals 100 e to the 0.05t, and then solve this equation for t. So 2 is e to the 0.05t, and then take natural logs. Natural log of 2 is 0.05t, and then multiply both sides by 20, I guess. 20 natural log 2 equals t. And now we can get a decimal approximation for the time that it takes for this population to double. So 20 times natural log 2, I get t is about 13.86, and this is in years since our population growth rate was in years to begin with. So this population is going to double in about 13.86 years. The other question that I posed was, what is the long-term behavior of this population? And that's really asking what happens when time goes to infinity, right? Long-term means when time goes on a long way. So limit as t goes to infinity of p of t. So this is the limit as t goes to infinity of 100 times e to the 0.05t. But in this exponential, when t goes to infinity, this exponential also goes to infinity. And so this whole limit is infinity. And that's actually, a bit of a problem as far as the realism of this description is concerned, because it doesn't really matter what the population is or what the environment is that the population is living in. There will always be some sort of practical limit to the size of the population based on the environment, right? This description of the population just sort of assumes that there's no limit to how large the population can grow. But there's always some kind of limit to how large the population can grow. If nothing else, it's you're limited by the number of individuals you can fit in the environment. So we need to somehow modify this differential equation to limit the growth rate. And the idea of a maximum population that the environment can support, that's called a carrying capacity. So what we need to do is, in addition to having some sort of natural continuous proportional growth rate, which we'll call R, we need to also somehow add to this description a maximum number of individuals, k, that the environment can support. So our initial description of this population was dp dt equals the growth rate times p, right? So what we need to do is we need to figure out a way to make it so that when the population gets to size k, it stops growing, right? So we need to modify this function so that when p is equal to k, dp dt is equal to 0. And maybe it's not entirely clear how to do that, but one way we can come up with a way to do that is think of this equation, rather than just a differential equation, think of this as defining a function. So we could imagine that this is a function of p, and then it would look like this. So on the horizontal axis we have p, and on the vertical axis we have the function, f of p. Remember, f of p is really the derivative. So what we're drawing here is a graph of p versus its own rate of change. So this is not, notice that time doesn't show up in this picture explicitly anywhere. So the way that we have this differential equation written right now, our function is just a constant times p. So this constant on this graph, this constant is going to look like a slope. So it's something like this. So slope here is r. So what we need to do is modify this so that somehow this graph gets back down to 0 when we reach population k, right? When the population is k, we want the rate of change to be 0 again. So it needs to come back down to 0. But if you look at this part of this graph that I've drawn, it looks sort of like it's making a parabola, right? At least on this interval from 0 to k, it sort of curves up and then back down. So one way to get at what we might, one way to modify this differential equation is just write a parabola that crosses the horizontal axis at 0, which this already does, but also at k. So what we could do here is multiply by some extra factor here that is 0 when the population is k. And there's actually many ways to do that. So one first guess on how you could do that is just put p minus k right here. But this has some issues. So the main issue with this is if we look at what happens near 0, so when the population is small. When the population is small, this differential equation becomes dp dt is about r times p But if p is near 0, then this stuff in parentheses here is minus k, right? Because p is almost 0. So when the population is small, dp dt is approximately minus krp. But this isn't right, because what this is saying is when the population is small, the population gets smaller because it has this negative growth rate. So that's backwards. When the population is small, the population should grow. So that's one problem. The other problem is when the population is small, the growth of the population isn't restricted by the environment, really, because we're so far away from the carrying capacity, right? There are so few individuals, they don't really have to compete for resources very much. So when the population is near 0, the proportional growth rate should be the natural growth rate, r, but it isn't. Here it's k times r instead. So this differential equation that we wrote down, r times p minus k, this doesn't quite do what we want, right? It produces, when the population is equal to k, it makes the dp dt 0, but it has some other undesirable features. So what could we do? Well, this minus sign, that's actually easy to fix. All we need to do is turn this around. Right? That is essentially multiplying this right-hand side by minus 1. So now if we plug in p equals 0 right here, we get r times p times positive k. So now when p is near 0, we get dp dt equals rkp. And that's bigger than 0. So if our population is small, it's going to grow, which is good. But still, it's growing at the rate r times k instead of just r. So, right, the issue with this extra factor that we've added is, in addition to producing the 0 we wanted when k is equal to p, it also sort of scales up the whole thing by a factor k. So maybe one more thing we could try is, since we accidentally scaled this up by k, maybe we should take this equation and scale it down by k as well, by dividing by k. If we simplify the right-hand side, this gives us r times p times 1 minus p over k. So let's see how this differential equation works. So dp dt is r times p times 1 minus p over k. So first of all, if we graph p versus dp dt, right, this, if we multiply this out, this is a parabola, so it has two zeros. One of them is at p equals 0 right here, and the other one is at k, right, just like we wanted. If we multiplied this out, we would see the leading coefficient, the coefficient on the p squared term, is negative, and that means that this parabola opens down, so it's like this. Okay, this kind of makes sense because when the population is very small, the growth rate is small because the population is so small. When the population is close to the carrying capacity, the growth rate is small just because there's not much room left to grow. And in between, the growth rate is bigger because there are enough individuals to get population growing, but also there's enough room left in the environment that there's space for more individuals. Okay, so this graph is sort of promising. Also, when p is near 0, we get dp dt is approximately r times p times 1 minus 0 over k, and so we just get r times p. So for this equation, when p is near 0, the growth rate looks like our natural growth rate. And remember, that's something that we expected from a good population model. When the population is small, it should grow in an unrestrained fashion. So this this differential equation, dp dt, equals r times p times 1 minus p over k, where k is the carrying capacity. This is a sort of a very common way to describe the growth of a population that's somehow limited by its environment, and k is that carrying capacity, the limit in the environment. So this equation is a pretty common population model, and so it gets a name. It happens to be called the logistic equation for population growth, or the logistic model. All right, so we will solve this. Eventually, but even before we solve it, there's a really nice way to analyze this kind of equation. Now, something you might notice about this equation is that on the right-hand side, there's no t. That kind of equation is called autonomous. And for autonomous equations, there's a really nice way to analyze certain solutions for this equation. So let's have a look at that trick. So here's our logistic equation, and what we could ask is, are there solutions that don't change? In other words, solutions that just sit at a certain population value and never grow and never shrink. These kinds of solutions are called equilibrium solutions. Right? Equilibrium just means everything sort of is balanced, and that's the idea that we're getting at. We're looking for populations where the tendency to grow is limited by something else, and so the population stays the same. Well, if a solution doesn't change in size, that means that dp dt is 0. So if we're looking for equilibrium solutions, we can just set dp dt equal to 0. But in this equation, if we do that, we get 0 equals r times p times 1 minus p over k. And there's no t here. Since there's no t in this equation, we can just solve this equation for p to find our equilibrium solutions. Of course, since it's factored already, all we need to do is set this first factor equal to 0, or set this second factor equal to 0, and then solve. So the first one just gives us p equals 0. That's one equilibrium solution. And the other equilibrium solution, if we solve this equation, we get p equals k. And that's the equilibrium solution that we expected, right? K is the carrying capacity, so you'd think if we have a population that is at the carrying capacity, it won't be able to grow because that would push the population past the carrying capacity. And it shouldn't shrink because the carrying capacity is K, so there are enough resources in the environment to support the population that exists. It's just that the population can't get any bigger. So it makes sense that we get these two equilibrium solutions. One common way to draw this sort of differential equation that's autonomous is to just draw a p-axis. We can put our equilibrium solutions on here. So 0 is one of them, and k is another. And what we can do to get sort of a general understanding of what solutions look like is we can decorate this p-axis with arrows indicating which direction solutions move. For example, suppose a solution starts here. Okay, so this is bigger than 0 but less than k. Maybe say it's k over 2. That's between k and 0. So if we take our differential equation and we plug k over 2 in here for p, right, we get r over 2 times k and then times 1 minus k over 2 over k, that's a half. And so this whole mess turns into rk over 4. And this is positive, right? R is a positive constant, k is a positive constant. So if we start out at k over 2, then the solution that we get will be increasing because its derivative is positive. And so we're increasing, so I'll put an arrow like this pointing up. Because if we start at k over 2, our solution increases. If we started with a value bigger than k, say 2k, if we ran the whole argument again, we'd find that this differential equation gives us a negative result. I guess why don't we do that? So dp dt, so this one was up here, was when p is k over 2. So now we're doing when p is 2k. So we get r times 2k times 1 minus 2k over k. So this is minus 2kr. And it's negative, right? So if we start above the carrying capacity, then our population will decrease. So I'll draw this arrow going down. To see what would happen if p is negative, we could plug in a negative value to see what happens, but since populations can't be negative, we don't really care what happens when p is negative. So in fact, you would get a decreasing like this, but down here, it's unrealistic, just because you can't have negative populations. So this picture, right, let's summarize what this picture is telling us. So first, we have the equilibria. There's an equilibrium at 0, and there's an equilibrium at k. Also, this picture tells us what happens to all the other solutions. Any solution that starts between 0 and k increases towards k. Any solution that starts above k decreases towards k. Also, any solution that starts below 0 decreases, but that doesn't really concern us since that's unrealistic. This is actually enough information to sketch solutions for this differential equation without actually solving the solutions, or without finding the solutions exactly. So now let's sketch graphs in the t-p plane. So here we're actually sketching solutions, so the population functions. We know that if we start at 0, the population stays at 0, so one solution looks like this. Also, we know if we start at population k, we stay at population k, so that looks like this. Right, now let's look at, so those are the two equilibrium solutions. Now let's look at other solutions. So suppose we started, say here, above 0 but below k. We know that the population is going to increase, so it will get closer to k. And here we have to use intuition a little bit. So it stands to reason that the closer we get to k, the slower we have to grow. And the reason that that has to be true is if we didn't slow down, eventually we would hit k. But it's actually a fact that these solutions can't cross. I won't prove that, but it's true. So since we keep increasing, but we can't actually touch this horizontal line at height k, we have to slow down like this. And in fact, we could run time backwards and decrease towards population 0. But again, we can't touch population 0 because these solutions never cross. So we get a solution like this. And in fact, for all the other starting values of population, there's a similar graph like this. So all of the solutions between 0 and k look something like this. They sort of start growing slowly, and then they start growing a bit faster, and then as you get close to the carrying capacity, they slow down again. If you start above k, well, this picture tells us that you're going to decrease towards k, so that's going to look something like this. And as we go to the left, there's sort of no limit off to the left, so it just keeps going up like that. Below the t-axis, we won't bother sketching those solutions since those aren't realistic. So you can see there's a lot of information we can extract from just this picture that tells us the equilibrium solutions, and also for each interval between equilibria, whether solutions are increasing or decreasing. So this is a pretty handy picture. This picture is called the phase line for the differential equation.